For almost all of human history, the age of our world was a complete mystery. But the story of how we finally pinned down its birthday, well, it's one of the greatest scientific detective stories ever told. So how did we get from just guessing to a number we're absolutely sure of? Believe it or not, our story starts right here. And not with a geologist chipping away at rocks, but with a scholar hunched over a desk. See, back in the mid-1600s, people made a really serious attempt to figure out the world's age using the most trusted historical source they had, which was the Bible. And this is what they came up with. A very specific date, right? It was calculated by Archbishop James Ussher, a really respected scholar at the time. He painstakingly went through and added up all the genealogies in the Old Testament and landed on that exact date. And for the next couple of hundred years, that was it. A 6,000-year-old Earth was pretty much the accepted fact in a lot of the Western world. Okay, so how in the world did we get from 6,000 years to 4.54 billion years? I mean, that's not just a small correction, that's a monumental leap in our understanding. It took a total revolution in how we even think about our planet, seeing it not as some static, recent creation, but as this dynamic, incredibly ancient place. So, yeah, how did we make that jump? The first big step was to, put down the ancient texts and start looking at the actual evidence written into the Earth itself. And it turns out the rocks were beginning to tell a very, very different story. And this is when our timeline of understanding really started to stretch out. We go from Ussher's 6,000 years to the late 1700s, where this guy, the Comte de Buffon, did something pretty clever. He treated the Earth like a physics problem. He heated up little iron spheres, timed how long they took to cool, and then scaled that up for a planet-sized sphere. His estimate? At least 75,000 years. Then you fast forward to the early 1800s, and you've got geologists like Charles Lyell looking at things like erosion. He saw how slowly rivers carve out canyons, and he realized there's just no way this happens in thousands of years. We're talking millions of years. But just as geologists were getting all comfortable with this awesome new idea of deep time, a giant of 19th century physics came along and just slammed on the brakes. Hard. And it set up one of the biggest scientific showdowns of the century. So here was the big debate. On one side, you had Lord Kelvin, an absolute genius of physics. He said, look, it's simple. The Earth started as a molten ball of rock, right? The laws of thermodynamics tell us exactly how fast it should cool down. And based on that, it can't be more than, say, 20 to 40 million years old. And his math was flawless. But on the other side, you had the geologists and biologists, guys like Charles Darwin, looking at the evidence in the ground, saying, hold on, for mountains to rise and erode, for life to evolve, we need hundreds of millions of years. So you had perfect physics clashing with observable reality. And Kelvin was so sure he was right. He famously said that geologists claiming these huge spans of time are like people who are possessed of a jewel which they are forbidden to wear. Basically, he was telling them their deep time was a beautiful fantasy they weren't allowed to have. And because he was such a respected figure, his arguments really did stall progress for decades. Geologists had to twist themselves into knots trying to make their observations fit into his tiny 20 million year window. The stalemate was finally broken by something that came completely out of left field. It was a discovery that didn't just question Kelvin's logic, it completely blew it up. And it gave scientists the perfect tool they needed, a stopwatch built right into the atoms of the Earth. And what was that game changer? Radioactivity. This was the missing piece of the whole puzzle. Discoveries by people like Becquerel and Marie and Pierre Curie showed that certain elements, like uranium, are constantly breaking down. And as they decay, they release heat. This was the one thing Kelvin's calculations missed. The Earth wasn't just a cooling rock. It had its own internal heat engine, a furnace constantly generating warmth. And that meant it could be way, way older than Kelvin ever thought possible. But releasing heat wasn't even the coolest part. This process of decay, it gave us an incredible new tool. Scientists figured out that it happens at a perfectly steady, predictable rate. We call it a half-life. Basically, for any radioactive element, we know exactly how long it takes for half of the original parent atoms to turn into new, stable daughter atoms. Think about it. It's a perfect atomic clock. It starts ticking the second a mineral forms, and nothing can stop it or change its speed. Not heat, not pressure, nothing.
And just like that, geologists had this amazing new toolkit, a whole set of these atomic clocks. You've got uranium-238, which decays into lead-206 over a really, really long time, a half-life of almost 4.5 billion years, perfect for dating ancient rocks. Then there are others, like potassium-40 turning into argon-40, and of course the famous one, carbon-14, which has a much shorter half-life, so it's great for dating younger things. The method is brilliant in its simplicity. You just measure the ratio of the parent atoms to the daughter atoms, and boom, you can calculate exactly how long that clock's been ticking.
So, the tool was there. The atomic clock was discovered. But actually using it to get the true age of the entire planet, well, that took one of the most obsessive, painstaking, and downright heroic efforts in the history of science. And it was all led by one guy, a geochemist named Claire Patterson. See, Patterson was smart. He knew he couldn't just find the oldest rock here on Earth and call it a day. Why? Because our planet is constantly churning. The crust gets melted down, reformed, recycled, and every time that happens, it resets those atomic clocks back to zero. So, to find the real starting gun for the solar system, he needed to find a rock that hadn't been touched since the very beginning. His target? Meteorites. This sounds straightforward, right? It wasn't. It turned into a 7-year-long nightmare. Every single sample he looked at was just hopelessly contaminated with modern lead. We're talking lead from gasoline, which was everywhere back then, lead from solder and pipes, from paint. It was in the air and the dust, everywhere. So to solve this, he literally had to invent the world's first clean room. He engineered this ultra-clean laboratory where he acid-washed everything, just to isolate a pure sample. His greatest enemy wasn't some complex scientific problem. It was microscopic dust. And then, finally, in 1953, he got it. After all that work, he successfully isolated the original lead from a piece of the Canyon Diablo meteorite. He ran the numbers, and the age he calculated was 4.55 billion years. Just imagine that moment. It was the very first time anyone in history knew the true reliable age of our world. And what's amazing is, that number has barely changed in over 70 years. He basically nailed it. But the story doesn't stop with that amazing number. Because in his obsessive quest to get rid of all that lead contamination, Patterson accidentally stumbled onto a massive modern-day crisis. He realized that what other scientists were calling normal background levels of lead wasn't normal at all. It was the result of massive industrial pollution. Because he had measured the true natural level in those ancient meteorites, he had a perfect baseline. And when he compared it to the modern world, he was absolutely horrified. And this completely changed him. It turned him from a geochemist into a public health crusader. He spent the rest of his career proving that industrial lead was actively poisoning people, especially children. He took on the incredibly powerful lead and gasoline industries for decades, and it was his meticulous, undeniable science that became the driving force behind the Clean Air Act and eventually the worldwide ban on leaded gasoline. He didn't just date the planet. His work has protected the health of millions. So Patterson gave us this incredible number. But why are we still so confident in it today? I mean, really, really confident. Well, it's because his measurement from that meteorite isn't the only piece of the puzzle. It's just one part of a much bigger picture where everything clicks together perfectly. Here's why the number is so solid. We have all these independent lines of proof. For instance, the absolute oldest bits of Earth's crust we've ever found are these tiny zircon crystals in Australia. Their age, 4.4 billion years. The moon rocks the Apollo astronauts brought back, they clock in at around 4.5 billion years. And our models of how stars work, based on totally different physics, tell us the sun is about 4.6 billion years old. It all lines up. Plus, we can look at stars exploding billions of light years away and see that the laws of physics have worked the exact same way throughout cosmic history. Everything points to the same conclusion. So you see, it's not a guess. It's a conclusion drawn from geology, chemistry, physics, and astronomy, all telling us the exact same story. They're all using different methods, looking at different things, from tiny crystals here on Earth to moon rocks to our own sun, and they all converge on that same number. That's when you know you're onto something real. Which just leaves us with this final kind of profound thought, doesn't it? The quest to find our planet's beginning, born from pure, simple curiosity, accidentally gave us the exact tools we needed to protect its future. It's just an incredible reminder that sometimes the most important discoveries are the ones you weren't even looking for.